Hello, 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 hello. Great. Hi, everyone. How are you? Sorry, I'm just setting up right now. Give me a second. What are you all doing inside looking at technology when the weather is unbelievably gorgeous outside? You should all be ashamed. I come from Seattle, you know? Like, though we get this, we don't get this all the time. I would be outside taking advantage of it. I am David Aronchick. I am a product manager on Google Container Engine and a part of the product management group for Kubernetes. Look at that. There you go. And we'll do you. OK, thank you. All right, we'll do it by hand. I say the product management group because it's so important for us to recognize that this is very much a community-driven project. Our goal is that other folks basically do all the contributions, or certainly a significant portion of them. And right now, we have actually achieved at least that portion of our goal. We have over 50% of people from the community doing contributions to the core project. This is something that was inconceivable for us, 2.5 years when we launched. Our goal was obviously have this be owned by the community, but we always thought that this was going to be a challenge for folks. And we couldn't be happier to see the kind of people who are embracing Kubernetes, and not just embracing it and using it, but actually contributing to it. So with that, you're not going to work, are you? OK. So as I mentioned, Kubernetes has just been on fire the past 2.5 years. We couldn't be more ecstatic about it. When you think about these companies using Kubernetes and under the hood using Docker as the container runtime, these are basically who's who for large enterprises doing this. Whether or not it's Pokemon Go with their mobile app game, Walmart runs their public websites on Kubernetes and Docker. New York Times, Concur, Ticketmaster. These are companies that you wouldn't expect to adopt a new technology and really a new way of rolling out software as quickly as they have. But I think it just goes to show the level of value that they see. And when we say level of value, we mean things like this. It's incredibly fast to deploy new software. I think that the world is really being set based on how quickly you're able to respond to customer demand. And we see people move from a rollout every week or every 2 weeks to 20 to 50 times a day. You see it being scalable. Pokemon Go was able to achieve $1 billion in revenue, the fastest app ever to do so. And they did it all on the back of an enormous deployment, all running against Kubernetes. And then finally, it's open. It runs everywhere. Anywhere that you can run Docker, with some small exceptions, you can run Kubernetes. And again, we are very, very proud of that. And when we say run Kubernetes, we really want to democratize the work that we've done inside of Google. At Google, everything in the world runs inside a container. And we use our own internal version of Kubernetes called Borg, which is designed to scale and enable developers to move extremely quickly. And our goal with Kubernetes is to give everyone the power to run agile, reliable, distributed systems at scale. Not just a container, but in fact an entire system and an entire application and an entire system. You can see here what our growth has been over the past 6 months, or excuse me, 6 months, 2.5 years. We've just released Kubernetes 1.6. We're on a 3-month time window for releasing new versions extremely regularly, as you see there. And as I said, we have broad adoption of Kubernetes. 5,000 commits in 1.6 alone, 10% increase in number of contributors, top 0.01 of GitHub projects, and over 5,000 projects based on Kubernetes hosted on GitHub. So with that, I'd love to tell you a little bit about Kubernetes 1.6, which has, as I mentioned, just released. Some of the things that we focused on for Kubernetes 1.6, and this is just a small subset, are around our overall simplified setup, including multi-cluster setup, which is something that we know a lot of folks are doing. An increase in Kubernetes scale, improvements to our overall scheduling, and some very sophisticated scheduling for even the largest workloads to address. Using network policy to move containers around, giving you additional security constructs without having to resort to using IPs and firewalls. And then finally, using Helm for application deployment. And again, under the hood, it's all Docker, but by layering these constructs over the top, you're able to see a much greater utilization of your clusters, and it makes much more sense in a distributed systems context. Okay, so who has heard setting up a Kubernetes cluster is hard? Raise your hand. Come on. All right, the rest of you are liars. The truth is that this was an area that we have known needed work for a long time, and we just wanted to get to it, wanted to get it right. And the reality is that we already have a very simple way of deploying Kubernetes today, and it's very reliable. It's kubeup, and it's a very simple script. The problem is that the second you needed any kind of configuration changes, you normally would have to divert from the happy path, and it required unrolling 2,000 lines of bash script. That is not ideal. Today, there are also many third-party tools which make it much easier, but the reality is that we didn't want to rely on those third-party tools for everything. We still think that they're great, things like COPS and AWS and many others. But what we wanted to do is solve a lot of the core problems, including things like cert exchange, joining nodes together, that everyone would have to do, and then rely on those third-party tools to really making it run great on other platforms. So the way that we have solved this is a new tool called kubeadm. This may look very familiar to you. The first thing you do is simply install a set of packages. You can see there all the Kubernetes components, of which there are 5, are installable from your standard repo. You then type a command, kubeadm init, which may be familiar to you. And at the end of it, you get a setup of your master node. And that's it. So your master is now set up and ready to go. You get an output of a last command with a secure token. You can pass that token in if you'd like, or you can have it auto-generated for you. And then once you do that, you go to your second VM, and you say you install those packages just like you did before, and you join it back to the master. And that's it. You have a Kubernetes cluster. Now, that's not everything. You'll want to set up things like persistent external disk. You'll want to set up load balancers and things like that. We can do some of that for you, but we really want to rely on platforms that understand the underlying cloud infrastructure. And that's why we do recommend using third-party tools or doing your own tools that understand your cloud better. Further, frequently you might want to do something more advanced, like deploy a daemon set. For those that don't know, a daemon set is where you have a single container that runs on every node of your system, one and only one. For example, maybe you want a proxy that uses an overlay network. Very common request. In this case, we have a single deployment here from Weave, and you can run that, and it'll run across all of your network. So that's kubeadm. Now, if you want to run similarly to the way Google does, instead of setting up just one cluster, you'll set up a second or a third cluster. But what we don't want to have happen is, as you set up those additional clusters, we don't want it to exponentially be more challenging to manage. Ideally, adding a second cluster will add a little bit of complexity. They always will. But we want it to be very gradual. And so what we need to do is we need to build a construct that overlays everything you see in your various clusters, so it's very easy to interact with them. In this case, prior to today, it's been somewhat challenging to do that. There are the exact same challenges that you ran when setting up a single cluster, you would have to run into when you're setting up what we call a federation around certificate exchange and permissions and things like that. But we've really tried to address that. And the way we did is with another tool called kubefed. And you might notice a similar naming scheme that we're developing here. So in this case, I log in just any node, it could be even my command line on my Mac, And using the credentials I've already downloaded to authorize my interaction with the Kubernetes cluster, I say kubenet fellowship, that's the name of the federation. A host cluster, the federation is hosted in a single cluster. And then I need an external DNS zone name. And that's because all the clusters need to talk to each other, so they need a way to resolve. In that case, the federation has now been created. I switch my command, my client-side command, from where I am today to using that federation as the endpoint. And then on my second cluster, all I do is I say join that second cluster to the initial federation context. Now, you might ask, how do I get permissions to that? I've already gone and downloaded those credentials and certs so that I can talk to that second cluster. But other than that, it's set up. And that's it. Now I have a federation with 2 clusters joined together. And so if I want to deploy an application across those 2 clusters, it's just a single command. Just like I was previously talking to an API master in a single cluster, now I'm talking to a federation. And the federation is responsible for talking to both of the clusters. Any questions? Did I see something? All right. Please do jump in if you have anything. So now how do I connect clusters together? What you frequently see is clusters set up across multiple clouds, and you don't want that traffic going over the internet. Kubernetes does support right now direct peering or interconnect between the various clusters so that you can have a private layout. But you can see how it works here. Logically, this is how the layout looks. Atop, you have a federation control plane that has cross-cluster service discovery, geo-load balancing, cluster health checks to make sure things are up and running, and an overall federated API so that I can hand the exact same objects that I previously just handed to a single Kubernetes cluster to a Kubernetes federation API and have it deploy across all of them. Whether or not it's a single pod, which might contain 1 or more containers, whether or not it's a replica set, a daemon set, a deployment, anything like that. Additionally, you start to get into problems around multi-cloud deployments. So as I said before, we really don't want people to have to increase their overall administrative burden as they start adding these things together. And this is a real challenge. So let's say I have 2 clusters set up, one on Google Cloud, one on AWS, and I create an application description that includes a persistent disk backing. Today, I would have to name what that persistent backing is. In this case, let's say it's a GCE persistent disk. Well, that works if I hand it to the GCE cluster because it understands how to deploy a GCE persistent disk. If I do the exact same thing, but on an AWS cluster, AWS has no idea what I'm talking about, and so it's going to fail. Make sense? Now, what we want to do is we want to have a neutral way to describe this. And so what you do is you have a second person, or whoever set up the cluster in the first place, interact with each of the underlying clouds. So let's say this person says every cluster should have 1 terabyte of persistent disk that they can use as they would like. What you do then is that person first talks to the GCE API, or the GCP, Google Cloud Platform API, and creates a persistent disk and attaches it to the cluster. And then they talk to the AWS API, and they do that as a one-time action. Then, instead of creating a as part of my application, a GCE PD, I create something called a persistent volume claim. And it simply says, I want 100 gigabytes of that underlying persistent disk that you already know about and know how to provision. So you do that, and each of the clusters knows how to go out and get that 100 gigabytes of persistent disk and take it offline. It also means that the system is smart enough to know that there are now only 900 gigabytes remaining, and if that's not available, it'll fail in a much more intelligent way. Any questions? OK. Next is around scaling. Kubernetes previously was capped at 2,000 nodes. In fact, we've heard and we've talked to many people who have actually run many more than that. But we have a very strict SLO policy, and unless we're able to spin up clusters, spin up pods, and schedule with a sub 5-second latency a across the entire operation, we didn't pass it. We've done a ton of work in Kubernetes 1.6, including a bunch of work with the CoreOS etcd folks to now support 5,000 nodes with a 99 API latency of less than 1 second and a 99% pod startup time of less than 1 second. So, and just to be clear on what kind of scalability this is, Pokemon Go was able to launch their world-breaking app when we hadn't yet reached this challenge. So we're already 150% better than even Pokemon Go's sized clusters. Yeah, of course. So we don't have specific SLA or SLOs around that. Right now, it will be a long time. And the reason is because we do it serially. We do not yet have parallel node upgrades. That said, there is that's with the built-in functionality. The best practice when it comes to spinning up nodes is actually not to do just one, to upgrade an existing cluster in place, but in fact to use something that's native to Google Container Engine, which is called a node pool. So what you would do is you would create a second node pool of size n, and you'd start to, you'd create, I don't know, call it 100 or something like that. And then you'd take 100 off of your existing 5,000 node pool, and it would naturally spread over. And then you do 100 up and 100 down, 100 up, 100 down. And you just do that continuously. That is a parallel operation and would work much better. By the way, that is a best practice for upgrading your clusters generally, even on a 5-node cluster. Instead of hitting upgrade, you have a second one, and you upgrade it automatically. Or you could use a brand new feature, which we have in Google Container Engine, which is auto upgrade, where we watch your nodes and upgrade them for you. And then you never even have to worry about it. Make sense? Any other questions? OK, so now I'd like to get into some sophisticated scheduling constructs. Particularly as you start to get into these very large clusters, you run into a whole bunch of problems that you may not have noticed before. Here we have roughly 4 key scheduling constructs that I'll walk you through. The first is what I call taints and tolerations. A taint is simply, think of it as a label for a node, a way to describe the node to the cluster in a way that the cluster can make sense when it comes to scheduling. And a toleration is a way to read and react to that. And I'll show you what that means in a second. Affinity, anti-affinity, that's where you may want to schedule to the same node, or you may want to never schedule to the same node. Forgiveness, and that's where, as you start to get into large clusters, you may not want to take action immediately if there's some underlying problem, and I'll show you why in a second. And then finally, disruption budget, and that goes to what you were saying, particularly as you get into larger clusters, you want to take more parallel actions, but unless you have something like disruption budget, you can get into a bad state. And again, I'll show you how that works. All right, so walking you through this is what a taint is. Today, if I take a pod, a random pod, that needs 4 gigabytes of RAM, and I have 3 nodes, one that has GPUs on it and 2 that don't, but they all have 4 gigabytes. When the scheduler schedules, it just schedules wherever it makes sense. And so let's say it's scheduled to that one with GPUs. When the second one comes along, it's going to either give up, which would actually be better than what often can also happen if you have it misconfigured, which is schedule in place without the GPUs, and then it has a bad time. The ideal is doing what you see here. So you say, I'm going to taint a node, this node number 1, and say that it has a taint on it that it says, hey, unless you require a GPU, please try not to schedule here. And so in that case, now I take that same pod 1. It was previously going to schedule everywhere, but instead it's going to skip that first one and go to number 2 because the scheduler now has awareness. And then when the second pod comes along, it prefers scheduling to the one that has GPU, and then it takes action. Make sense? You can do a lot of different things with this. I'll walk through some other scenarios. Oftentimes, maybe you have something where you want to always keep some CPUs in reserve for potentially higher value workloads. In this case, let's say I have a taint that goes across these two so that I can always make sure no matter what happens, I have this many CPUs available for my premium workload. I try and schedule those 2 premium pods. Maybe I don't care where they go as long as they always are able to schedule. And I do so. That third one comes down. And then when that regular pod tries to schedule, it will fail. Another idea, another reason that you might want to use this is, let's say you run a security scan, or you want to ensure that some basic packages have been installed, or something along those lines. Maybe there's a failure because it failed a tripwire. What you want to do is you apply taints to every node, and then when a pod comes along to try and schedule, you say, actually, there's nothing available to me. I'm just going to sit here waiting. And the node goes out. It contacts the TPM. The TPM says that everything's good. You remove the taint, and then it can be scheduled properly. And then here's a final one. Let's say you have hardware that is beginning to fail. Let's say the hard disk is beginning to report errors, or you're seeing some messages or something like that. You can apply a taint to an existing node and to ensure that nothing else gets scheduled there. And then you can kill the pod on there and schedule it to a new node. Any questions? Yeah. Still you? I can repeat the question if you want. It's easier.
Okay, one question about the taints. How do you apply a taint to a node? Can you apply it to a label so when the node comes up, it reads the label and automatically taints the node?
I think you would want to do that in a different way. You'd actually want to do it. I need to check best practice on that. I think what you would want to do is you would want, if every node that came up required this, then you would want to have it as part of the join process. However, if you only wanted it to apply to a certain label, everything in Kubernetes is based on labels. So what you would actually do is you would just add this label to the API server, and then when the node came up and had that label on it, the taint would automatically be applied. But I need to sort out exactly what the best practice is, so please do send me a mail and I'll follow up. Any other questions? Okay, so now affinity and anti-affinity. Very common request. Let's say you have something like a quorum-based app that requires a minimum of 2 things to run. Ideally, you would try not to schedule them to the same pod or the same node, because if that one node went down, then you would lose everything. What you see here is a cluster with 3 nodes. I have 2 CPUs over there, or excuse me, 2 pods are there already scheduled, different app. So what I do first is I set up something called pod anti-affinity, and I say match expressions, the app name, and then any arbitrary app name that I want. And so in this case, it schedules. It's first going to try and schedule where there's an available CPU. It's just standard spread scheduling. But then the next one theoretically could go anywhere. And in this case, it's going to preferentially not be scheduled to the same one. Now, I'm not saying don't schedule. I'm just saying prefer not to schedule. And that's because you want to, you don't want your app not to work. You just want to do your best to not schedule the same thing. And there's lots of flexibility here. You can do it by zone. You can do it by node, including things like zone, region, preemptible or not, SSD or not, all that good stuff. Or write your own. And pods are entirely label-based. So it's just whatever you want. So now we get into forgiveness. Forgiveness, like I said, is where you may have a situation, particularly on large fleets, where you lose connectivity or the node starts flapping a little bit, but it may just go away after a little bit. You have no idea why it is, and you don't want to be overly aggressive, particularly if pods take a long time to start up. So in this case, I'm going to simulate a network partition. So Right now, the node is going along, everything is working fine. And then all of a sudden, the partition happens. The API server is not able to communicate with the underlying node. And it's been 3 minutes, 4 minutes, 5 minutes. And only then, when it hits 5 minutes, do I treat the node or the pod, which has a 5-minute forgiveness on it, that as dead, and it moves on. But it still leaves the 30-minute one running because it hasn't heard anything back, and that's OK. It could rejoin, and everything could be happy. That 5-minute pod, though, if that node did come back and connect, it would have treated that pod as dead and made it so that killed it as soon as it joined. In addition, let's say I now get to 30 minutes. I'll kill that and reschedule it. So that's forgiveness. Again, as you start to get into large fleets, you're going to have this problem, random problems that crop up, from time to time. You have no idea, but you don't want to overreact. Right now, the Kubernetes scheduler is quite aggressive, and it'll reschedule the second it doesn't hear something. OK, so now let's do one more. This is the disruption budget. So as you were looking, upgrading a 5,000 node cluster, let's say you had 5,000 nodes, and for whatever reason, the first 10 nodes of the cluster had your app on it. Well, 10 nodes, that's a lot. You'd think you'd be pretty resilient. But if you wanted to start doing upgrades and you did them, 25 at a time, and you happen to grab the first 25, your app could die. So what you want to do is set up something called disruption budget. This tells the scheduler, hey, this app requires, at a minimum, 10 pods to be available at any given time. I'm going to simulate that here, or kind of highlight it by showing you 2 pods side by side that always at least one needs to be available. And so then I interact with the API server and say, it's time for me to upgrade all my nodes. I'd like you to evict A, because it's time to shut down. And it does. And then while A is shutting down, and it takes a long time, I'm going to ask it to kill B. But because it's aware that at least one has to be running at all times, it reports back and says it can't do it. And so it does that. It waits until A has been rescheduled, and then I can take action. Make sense? So those are some of the things we did around scheduling. Any questions all up? Oh, nothing? OK. Now let's talk network policy. So as I mentioned, network policy is one of these things. If you're using VMs today, it's actually pretty straightforward. You use firewall rules, IP-based scheduling, things like that. That's good, but when you get into containers, things get much, much harder. So here, if I was going to do a standard app, and I said VM1 should always be able to talk to VM2, VM2 should never be able to talk to VM1. Very standard policy, for example, a front-end website and a back-end database. The website needs to query the database. The database should never have to talk to the front end directly. So I set that up like this. IP rules, very straightforward. When I'm using containers and Kubernetes, this becomes much harder. For example, now let's say I schedule green and red both to the same machine, and they want to talk to each other. How do I set up rules? I can't use firewalls because the firewall rules on a single VM wouldn't apply. Or let's say I schedule a second container to a second one. Do I have to keep all the firewall rules up to sync? That's a problem. With network policy, I can use a label-based way to do this. So what I'm going to do here is, first I'm going to set a rule that says nothing can talk to anything. So everything is blocked. And then through a cascading rule, I'm then going to say green can talk to red. And it does so. And again, that's all label-based. I have no idea where these pods have been scheduled. They all run on the same they run on the same cluster, and they inherit the label-based network policy that's available. This is particularly powerful because let's say that second pod gets killed and restarted on a new one. It inherits that automatically. Any questions? All right, final thing, Helm. So one of the things that's particularly challenging is setting up complex apps. We don't want to build that into Kubernetes proper. We really want that to be a third-party tool that augments the additional system. And we're very happy to see that the community has centered on Helm. Helm is like a package manager for Kubernetes. So kind of like apt-get or yum or something like that. And it supports Kubernetes objects natively. So whether or not it's a deployment, daemon set, secret, config, multi-tier app, upgrades, it's all built in. So for example, here's Datadog. Datadog has a daemon set. That's an application that runs on only one time on every single node in the cluster. It even requires an API key and things like that. And it pulls straight from the Helm chart and rolls it out across 3 clusters simultaneously, or 3 nodes simultaneously. Further, Sappho. Sappho's been a supporter of Kubernetes for a long time. They have a very complicated app that connects to a whole series of different tools and gives you a single dashboard for managing your application. Managing your enterprise. In this case, they have a Tomcat front end, 3 replicas, 2 MySQL backends, and connect to all of the various tools you see here. And setting it up looks like that. Make sense? Questions? So what's next? Less, for large values of less. So what I mean by that is, part of what we want to do around Kubernetes is really to make it somewhat boring. We feel very strongly that there are some core objects that you need when it comes to running a Kubernetes cluster at scale or any distributed architecture at scale. And what we don't want to do is expand outside of the narrow swim lane that we've chosen for ourselves, basically where all you need for running a distributed application. But we don't want to build PaaSes. We don't want to build underlay networks. We don't want to build complicated orchestration systems and all that kind of stuff. We want those to exist, and we want them to be great, but we really want third parties and the ecosystem to fill it in. And that's why we work so hard to partner with all the folks out there to make those applications run great on Kubernetes. That said, we're certainly not done. You can see just a few of the things that we're going to be investing in here around GPUs. We're going to make a whole litany of security investments. We have a brand new secure logging infrastructure. We have a brand new managed node support, particularly around things called a brand new tool called the Node Problem Detector, which evaluates your nodes for its health across a whole series of things. Give you storage pluggability and scheduling. We'll give you additional runtime support for open source tooling and the container runtime interface. And finally, AWS IAM integration. And that's it. As you can see up there, Kubernetes open. We'd love your feedback. You tell us what you'd like us to work on next, or just jump in there if you have any questions. We try and be really, really responsive to all these questions and would love to have all of you helping us and making running containers at scale great. Any questions? Thoughts? Something? Really? Anyone running Kubernetes today? 1, 2, 3, 4, 5, 6. Keep going. 7. Higher. Anyone nervous about running Kubernetes today? 1. You can't be. He's a Googler. Anyone never going to run Kubernetes ever? It's okay. Got one up there. Like I said, we want to be really open. We love working with different folks. If you do have thoughts, ways that you'd like us to go, please let us know. This is like I said, a community that is very much not Google anymore. There's no single entity. If you came in and said, hey, come help us move in this direction, we'd love to listen. With that, thank you very much.